Hello, everybody. We are Group 9, and we are doing project on Bert fine-tuning for sentiment analysis. Our data set is Stanford Amazon reviews, and the method category is optimization algorithm. So first, I would be explaining that how Bert came into being. And earlier, LSTMs were used. And then in 2017, there was a research paper that is attention is all you need. And then we got the transformers. LSTM, they were based on concatenation, whereas transformers, they are bidirectional. I'll explain it with an example. For example, we are reading a book, and if we are reading a book sequentially, page by page, and we sometimes forget the earlier pages, and and also we don't get the context of those pages. So that is how LSTM works. It works sequentially, whereas transformers is like skimming through a book, just going through the relevant pages and using some attention mechanisms to understand the context of those highlighted versions. So that is how transformers work. So transformers, they have two parts, that is encoders and decoders. So when we stack those encoders, we get BERT, and when we stack the decoders, we get GPT. So how BERT actually solves the problem? First, we pre-train BERT to understand the language, and then we fine-tune BERT to learn a specific task. First, I would be discussing how we pre-train it. It is in two steps, that is mass language model and next sentence prediction. In mass language model, let's go with an example that Bert went to store and bought some apples. So what Bert will do is it will get the context of the apples, and then it will understand that the store here used is a mention to a retail store and not about storing something. So that's how MLM works. And next sentence prediction is it will keep in mind, it will remember the ordering of the sentences. That is, for example, she won the race, she celebrated. So it will remember this order. And the output we get is for MLM, we will get word vectors, and for NSP, we will get binary values. And then these word vectors, they are converted into distribution to train using cross entropy loss. And for the next phase, these are the steps we would be following. So over to Nimisha.
So for the next step, we are doing the data pre-processing, and this slide just kind of shows you what each review had in the data set. But for our model, our predictions are made based on only the score and the actual text of the review. So we are only using those parts of the data, and we're not using the rest of this, which was also in the data set. As a part of the pre-processing, we split the data into 1 MB, 10 MB, 100 MB, and 1 GB sets. We analyze the text so that we normalize the spaces so there's no inconsistencies. We remove any hyperlinks. We remove any unnecessary symbols. So the text is just important data that is relevant to the processing. We also split it into test, train, and validation sets, and we also do the tokenization. As a part of the tokenization, each word gets its own unique ID and it is treated as a mask, and these masks are what our model is trained over. And once the tokenization is done, we can now pass this data onto our model to train. As for our model, we use the Adam optimizer as the baseline and the Adam W optimizer as our optimized algorithm for our processing. And I will be passing it on to Gael.
So here it is for the fine-tuning BERT model. We decided to compare with Adam Optimizer, Adam W Optimizer, as described before. So basically, you want to focus yourself on these few values, especially for comparison. We want to compare the validation accuracy between the two models. And we decided to compare it between the first two epochs and between the last two epochs. And as you can see, we are winning like in average, we are winning some values with Adam W, but I would say it's not that significant. As you can see, you need to focus on average training loss, validation accuracy, There is not many difference on this aspect, but still, we can now focus on the model evaluation part, which is much more important and which give us much more important results here, especially for the times metrics. So we decided firstly to measure the time in our model evaluation for the two models. And as you can see here, if you take in consideration the sys time, so basically the system time while computing the training phase, you can see that there is a huge difference, like nearly divided by two in the system time for the training phase. So it's quite significant, as you can see. And here the optimization shows us that it is really doing its job, actually. And also for the wall time, as you can see, it has also been diminished. So it's also something we have to consider here. So great point for the optimizer here. And also for other type of model evaluation. So as you can see, we mentioned the time measurement, and here we are focusing on the machine learning basic metrics from the precision, recall, F1 score. And as you can see, the Adam W still does quite a good job, especially for the precision, the negative precision, which is significantly higher. And but for the positive values, as you can see, there is not that much difference. You can see that we can gain a little bit of recall with the optimizations, and we also gain a little bit of score of F1 score. So as a summary for the model evaluation, we can say that there is not big, there is not big significant scores, but as you can see, we clearly made a difference in this optimization process. So currently heading to
Next, we'll be looking at the tuning of the hyperparameter learning rates. So we took the four most commonly used learning rates. And as you can see, the one in the green line, which is the learning rate of 2 e raised to minus 0.5, gives us the best performance over the epochs. Uh, and then the learning rate of 5 e raised to minus 0.5 gives us the worst performance. The learning rate of like the one in blue and green are close to each other, but green slightly outperforms the blue one, so we went with the learning rate in the green color. And we have initialized both our optimizers before we started pre-training our models on them with this learning rate. So after doing that, these are our baseline and the optimized version conversion curves. So as you can see, we have training loss on the y-axis and the epochs on the x-axis. And the optimized version for the 1 MB data set converges at around 6th epoch, but there is no convergence for the baseline. Uh, and then for the validation accuracy epoch curve, we can see that the optimized version outperforms the baseline version like at one epoch before the baseline version. And similar trend is also observed for the 10 MB data. So even though no convergence is achieved within 8 epochs for the baseline and the optimized version, you can see that for the epoch 4, the value for the baseline error and the value for the optimized error, like the value of the optimized error at epoch 4 is equal to the value of the error of baseline and epoch 5. And in the validation accuracy versus epoch curve, you can observe that the convergence is achieved for optimized model at epoch 5, while for the baseline model, it is achieved at epoch 6. So the goal of these plots was to showcase that the optimized version achieves convergence before the baseline model, and the graphs clearly indicate that that is the case with our model. And the next are the performance plots. So we have worked with 1 MB and 10 MB data. We have also tried running the models on the 100 MB and the 1 GB data, but even with small data sets like 10 MB, one training of 8 epochs would take about 2 to 2.5 hours, and we had to do it multiple times. And we have also ran it for 10 MBs, which was around like which was not done even in 10 hours. So the results that we have included are for 1 MB and 10 MBs. And as you can see over here, the optimized version outperforms the baseline slightly. There is no major difference, but at least in accuracy, F1 score, and recall, the optimized version is better than the baseline version for 1 MB data. And for 10 MB data, they are nearly the same. And that'll be all from our side. Thank you.